All right. Okay. So we're going to look at the left-hand side of the equation on Newton's law. So let's just remind ourselves about Newton's law. We have F net equals m times a. All right. So far you've just been given like, okay, here's the acceleration, here's the mass. What is the net force? Okay. Now, the net force is the vector sum of all the forces that are acting on an object. Okay? So you have to add them all up to find out what the net force is. And we can do that in a variety of contexts, but the first thing that you need to be familiar with is how to identify and draw all the forces that are acting on an object. Okay? So let's just practice that with a couple of examples, and then I'm going to pass out these worksheets, and we can practice going through some of those. Okay. So this is called a free body diagram. Okay. A free body diagram is a diagram that labels and illustrates all the forces that are acting on an object. Okay? So let's just take an example of like an airplane. Okay? So let me just sketch up an airplane. There it is. Flying through the air. Okay, like that. All right, there it is. So up is this way, right? And it's flying in this direction. So it is flying. It's in the air, okay? So what forces are acting on the airplane? Let's just think about it. What forces would be acting on the airplane? Drag. Okay. What is the direction for drag? Against where it's moving. It's not against where it's accelerating, it's against where it's moving. Because the plane could be slowing down, but the drag is still coming from the same direction, right? So drag always opposes the motion, okay? So when it's flying through the air, there's going to be a drag force vector like this. So we're just going to label it. So we put a point on the airplane, and we draw an arrow, and we label that. That's drag, okay? All right. What else is forces are acting on the plane? Gravity. Okay, so gravity is acting straight down. And the force of gravity is mass times the acceleration due to gravity, okay? M times lowercase g. Do you guys recall what g is? You remember, Merritt? What is g? Reagan, you remember? No. Phoebe, you remember? No. Hannah's not here. Alan, you remember? We're recording this for Hannah. Hi, Hannah. Okay. No? Lola? Grace? Jack? You probably don't remember because you didn't do your homework. Elias? It is 9.8 meters per second squared. Yeah, 9.8. So G is 9.8 meters per second squared. So the force of gravity on any object on Earth, okay, is that object's mass times the acceleration due to gravity, which is 9.8 meters per second squared. Okay, all right, let's go back to the plane. What other forces are acting on the plane? I would hope there are some more forces, right? Because if these are the only two forces, what's about to happen to this plane? It's going to fall out of the sky.
Is lift the one that's going up?
Yeah, there's got to be some kind of lift. All right? It's got to stay in the air, right? There's got to be a force that is causing the plane not to fall out of the sky. Okay? All right. Anything else? Are we missing anything? Is this plane going to get where it's going, Lola? Why not?
Because there's no force pulling it forward.
Yeah, there's no force. So we need a force pushing the plane forward, okay? So we'll just label that thrust. Okay? So you could label it different things, you know, the force of the engine pushing it forward or whatever, right? So I'm not as concerned about whether or not you can label all of these. I mean, you should be able to label gravity. But if you called lift something else, I mean, that's not a big deal, right? There's an upward force that's keeping the plane out of, you know, from falling out of the sky, right? We want to identify that, and we can label it the force that keeps it from falling out of the sky, right? We can just label it like that. So this is a free body diagram, okay? And all we need to be able to do is draw them like this. Let's take a look at one more example, and then I'll let you work a few examples. Okay. So let's say we have a skier skiing down a slope. Let's sketch up the slope. That's a pretty steep slope. This skier is going to crash and burn, but that's okay. All right, let's draw the skier. There's the skier, okay. Let's give it one more leg. Okay, there we go. There's the skier. Okay, what forces are acting on the skier? Gravity, that's right. So we're going to so we just illustrate a little dot, and that's gravity. So this is gravity. Okay? What else? Normal. What's the direction for the normal force, Phoebe? Up and which way up? Just straight up? It's perpendicular to the surface. The surface is the skiing surface. So we want to draw one that's perpendicular to the surface. Remember, the normal force is always perpendicular to the surface. Okay. All right, and then what else?
There's drag and stuff.
Yeah, there's some kind of drag / friction, etc., that's opposing the motion. Thrust. What's thrust doing? I've never seen a skier with a jetpack with thrust. But that's an interesting idea. No, what force causes the skier to go downhill? Gravity. Yeah, it's gravity. But it's not all of gravity. It's only the part of gravity that pulls down the hill. Okay? So there is a piece of gravity that pulls down the hill. We're not going to learn how to quantify that, okay? We just want to identify the forces and label them like this, okay? So, what is the direction of the normal force? It's always perpendicular to the surface. Always perpendicular to the surface. So you find the surface, you find what's perpendicular to it, and you draw it in that direction. Okay. All right. Okay, any questions about this? Let's practice this. There aren't any like homework problems on this because there's not a way to get you to like draw, but you have to draw free body diagrams to answer some of the questions. Okay. There's just not a specific way for you to calculate that. Or input free body diagrams. All right, there are two questions, number 1 and 2, that has you draw free body diagrams. And let's pause. All right. Okay. Let's take a look at these couple of questions. The first one is: a man is standing on a roof that makes an angle of 30 degrees with respect to horizontal. Okay, there's 30 degrees with respect to horizontal. Doesn't matter if you draw it this way or the other way. Like the guy could be standing on either side of the roof. Let's put him over here. So here he is, standing on the roof. Okay, and we want to label all the forces that are acting on him. All right, and so we have gravity acting straight down. So gravity should always be straight down, and the force of gravity is mass times acceleration due to gravity. It's mg. Okay, so I'll just abbreviate that as mg. Okay, and then I think everybody identified a normal force, and the normal force is perpendicular to this surface, like this. So there's the normal force. Okay, and then if there was no friction, Elias, what would happen to the man? He would slide down the roof, but he's just standing there. There is no sliding down the roof. He's standing there. So what is it that keeps him from sliding down the roof? Static friction. Okay? So static friction. And in which direction is static friction operating? Opposite the way he would be sliding, yes. So it is parallel to the roof, parallel to the surface, because that's where he would be sliding in this direction. Static friction is keeping him up. So I'll illustrate that with a F with a subscript S for friction that is static. All right. Okay, and if he was over here, that would all be kind of the mirror image of that, right? So if you did the other side, it would just be the mirror image of it. Okay. Now, why doesn't he just go like what's opposing static friction, right? Yeah, gravity is, right? There's part of gravity is actually pulling this way. And that's what's opposing static friction, okay? So there are only three forces acting on the man: normal, static friction, and gravity. And it's the piece of gravity that kind of pulls down the slanted roof that is opposing friction, or that friction is opposing. Okay. All right, the other one, a woman is standing in an elevator that is accelerating upward. Draw the free body diagram of the forces acting on the woman. Okay, so let's draw our elevator. Here's the elevator. Here's the woman. Okay, and what forces are acting on the woman? Gravity. And which way is gravity? Down. Gravity is down. mg. And then what else is acting on the woman? Normal force. Now, which of those forces is bigger? Gravity or the normal force?
Well, considering she's not falling through the elevator, it'd be normal, right?
No.
Gravity?
No.
Oh.
It is the normal force, but not considering that she's not falling through. It's considering the fact that she's accelerating upward. Right? She is accelerating, isn't that what it says?
Yeah.
She's accelerating upward, which means the normal force has to be bigger than gravity. Why does the normal force have to be bigger than gravity? Because she would be crushed. Because she's experiencing a net force. She's accelerating. A is not zero. A is up. Okay? that means that the net force has to be up. Does that make sense? Okay. So that's how, we can actually illustrate the free body diagram quantitatively if we know what those forces are. We can draw them as their lengths. Larger forces are longer arrows. Okay, so let's take a look at this lady real quick. So we need to be able to solve Newton's laws problems using two forces, right? So all the quantitative stuff that you're going to do is one-dimensional Newton's law problems, okay? Not two-dimensional Newton's law problems. That's what you would get in a physics class. We're doing one-dimensional Newton's law problems, okay? And if we want to calculate the net force acting on this woman, okay, and she's accelerating upward, the first thing that we want to do is add the forces up, okay? Now, do you guys remember adding vectors? You guys remember that? How do you add vectors? You guys remember? Jack, you remember? Did you ever do that homework? You don't remember? Grace, do you remember? No. Okay, when we add vectors, we take this normal force, and we go from the start of the normal force to the end of the normal force, and we put gravity right here like this. So we would move gravity like that. That way we can add the two vectors together. And then the net force vector starts at the very beginning and goes to the end like that. Okay? So you did this like with an ant crawling around on a piece of paper or something, and some of that kind of stuff, right? So forces are just other vectors that we can add together like that. Okay? Now, if we're just doing a one-dimensional problem, then these vectors add together just like regular numbers. In other words, I've got the normal force, and I'm subtracting gravity. You see that? Normal force minus gravity. Okay, so whenever you're calculating the net force, you want to define a positive direction. And here's the key. The positive direction points in the same direction as acceleration. Okay, now this isn't like mathematically required, but it sure is convenient. Okay, so this is what I want you to do. You need to look at this problem right here. This woman is accelerating upward. So since she's accelerating upward, up is the positive direction. If she was accelerating downward, what would be the positive direction, Phoebe? That's right. If she was accelerating to the right, what would the positive direction be, Reagan? To the right, right? So whatever the direction is of the acceleration vector, that's the positive direction, okay? But Lola, what if she's not accelerating? What if her acceleration is 0? Then you can pick whatever you want for the positive direction. All right? If there's no acceleration vector, then just choose up to be positive, right to be positive. It doesn't matter, okay? So, but if there is acceleration, and how do we know if there's acceleration? What's changing if there's acceleration? velocity. Velocity is changing if there's acceleration. How can velocity change? It can change in magnitude. You can speed up, you can slow down, and it can change in direction. You can turn to the left, you can turn to the right. So if either or both of those cases are true, velocity, you're changing direction or you're changing speed, then there is acceleration. Okay? All right. Let's go back here. So this woman, up is the positive direction. Okay? So let me just say that. Up is positive. Since up is positive, I'm going to take the normal force and subtract gravity. This is the net force. The net force is where you're taking the positive force and subtracting the negative force. Okay? This is the left-hand side of the equation. What's the right-hand side of the equation? It is the mass times acceleration. So over here on the right side of the equation, we're going to put mass times acceleration. So we can add forces together on the left-hand side of the equation, like this. Well, add, we're subtracting because they're in opposite directions, but if they were both in the same direction, we just add them together. And then that's going to equal mass times acceleration. All right? So in your new homework set, this is the kind of equation that you're going to work with, where you are going to solve for what's the normal force, or what is the friction force, or what's the pushing force, or that kind of stuff, okay? All right, so what I want you to do now, armed with this information, is I want you to answer questions 3 and 4 on the worksheet. Half of it, that's good. All right, so let me just kind of show you how to solve this, and then maybe for number 4, you'll see kind of how this works, okay? All right, so we've got an incline, and a puck is sliding down the incline. So let's just illustrate that. Here's my incline. Here's the puck sliding down the incline like this, okay? It is 0.1 kilograms. So I'm going to go ahead and label that as something that I'm given. So the mass of the puck is 0.1 kilograms. Okay, I'll go ahead and put that in there. And it's sliding down an incline with an acceleration of 2 meters per second squared. I'll go ahead and list that too. Acceleration is 2 meters per second squared. Okay, so I've got those two things. And in which the force of gravity along the incline is 0.3 newtons. So that's telling me that the piece of gravity that's pulling down is 0.3 newtons. So I'm going to label this 0.3 newtons. Okay? And that is the piece of gravity that is pulling down the incline, right? Okay, so let's keep going. What is the friction force acting on the puck? Well, what direction is the friction force going to act? Opposite the motion, right? So we're going to put that here. This is friction. And because it is sliding, what kind of friction is that? Kinetic friction, that's right. So it's kinetic friction. Okay, and so then we know that this piece right here is 0.3 newtons. Now, what is the positive direction in this case? Down the incline. Okay, I'm going to label that on this is the positive. That's the positive direction. That's important because whenever I add up my forces, I have to add them up with the positive one minus the negative 1, okay? So now I'm going to write out my equation for the net force. Let's do that here. F net is equal to 0.3 newtons minus F. So this is the net force acting on the puck, right? So you notice what I did? Sketched it out. I illustrated the two forces that were acting on the puck. I found the positive direction. And then the net force is the positive force minus the negative force. Okay? So all the quantitative work that you're going to do in your homework is just like this. There's going to be two forces, one of them, I think I might have one of them where they're in the same direction, but you just have to look at the problem and then, assign your positive direction. Okay. All right, so this is the net force. And what does the net force equal according to Newton's second law? Mass times acceleration. Yeah. This equals mass times acceleration. Okay. Now, do I know what the mass is? I sure do. Do I know what the acceleration is? I do. Can go in right there. Okay. So we can go ahead and plug the rest of that stuff in. We're going to have 0.3 newtons minus F equals the mass, which is 0.1 kilograms, times the acceleration, which is 2 meters per second squared. Now at this point, it kind of turns into a math problem, doesn't it? What am I solving for? Yeah, the friction force, F. I want this right here. I want to solve for that. How do I solve for that? I got to get it by itself, okay? So the fact that it's subtracted, we can add it to the other side, right? I can do plus F on both sides. Let's do that. Plus F. And then I have 0.3 newtons equals, and then what's 0.1 times 2? What's 0.1 times 2? Do you need a calculator to do this, Elias? It's 0.2. Okay, thank you. Right, so this is 0.2 newtons. I'm going to just combine it so that I get 0.2. So that's what that becomes. And then now I got to solve for F. What should you do next? Yeah, subtract 0.2 newtons from both sides. And the force is 0.1 newtons. Okay, everybody see how to do that? Why don't you try the next one? The horizontal drag on a 1,000 kilogram plane is 2,000 newtons. What horizontal force from the propellers is needed to accelerate the plane at 3.5 meters per second squared? Okay, let's take a quick look at this next one, which is the plane. All right, so the plane has a drag force acting on it. So the horizontal drag on a 1,000 kilogram plane is 2,000 newtons. So here's the plane. Okay, and there is a drag force that's acting of 1,000 newtons. And then there's some force from the propellers that is pushing the plane forward, right? So I'll just call that F subscript P. You can call it X, it doesn't matter. But that's what we're looking for because it says What is the horizontal force from the propellers, right? What is that? Okay, and then it gives us the fact that the plane is 1,000 kilograms, and it is accelerating at 3.5 meters per second squared. Okay, so then we want to now set up Newton's second law, the net force acting. Okay, so we look at this. What's the positive direction? Positive direction is in the direction of acceleration. So we want that to be the positive direction. So then we'll do F subscript P minus 1,000 newtons equals, wait, is it 1,000 or 2,000? It's 2,000. Okay, so that equals the mass times acceleration. Again, we're just going to shove this stuff in right here. We're going to put the mass and the acceleration on the right-hand side of Newton's second law. So then we get this equation. What is 1,000 times 3.5? Did somebody have to use their calculator? Yes. Did you guys have to use your calculator for that? 3,500 newtons. That's the right-hand side of the equation. And, oh, I dropped a 0. There we go. Let's get that back in there. And then all we need to do for this is add 2,000 newtons to both sides to get FP on a side by itself. And then we get 5,500 newtons, all right? So every single one of your homework questions that is quantitative like this, it's going to be the exact same process. You're going to have two forces that are in the same dimension. Some of them are vertical, some of them are horizontal, some of them are slanted, like the puck going down an incline, but it's a one-dimensional problem, and you just have to, again, assign the positive direction, add up your forces, figure out what the unknown is, okay? So either this is unknown, or I think I might have acceleration being unknown in one, but just different things that you got to find, okay? Okay, any questions about that? All right, the last one is just where you're going to add forces together. This is exactly like the ant. You got a homework problem. I'd like to just, since you guys can go back and look at your ant stuff for that, but it's the same kind of thing. I give you a scale. You just work it out with a ruler, and you're going to measure the net force, okay, following the instructions. But I want to work on our lab back here, if that's okay. So let's head back and do the lab.